Okay. First of all, I would like to thank the organizing committee for organizing this nice conference and inviting me to present my work at this prestigious seat of learning. My name is Hafiz Muhammad Fahad, and at present I am enrolled in the PhD Mathematics program in the Department of Mathematics, Eastern Mediterranean University, Northern Cyprus. Today I will present one of my joint research works with Dr. Aaron Fernandez, titled Operational Calculus for the Riemann Liouville Fractional Derivative with respect to a function and its applications. By operational calculus, we mean Mikusiński's operational calculus. This is the agenda of the talk. First of all, I will give you a brief introduction about the history of fractional calculus. Then we will discuss the classical Mikusiński's approach, followed by some basic definitions of fractional calculus. Then I will present some highlights of one of our recent research works. And finally, we will conclude this presentation by giving some concluding remarks. So all of us are well aware of this history of fractional calculus. So I will just skip this slide. Okay, let's move on to the most important slide of my talk. And here we will discuss the key ideas of Mikusiński's operational calculus approach. This approach, the algorithm of Mikusiński's operational calculus approach consists of 5 main steps. Here, the step number 1 is we choose an appropriate function space and make it a ring under some algebraic operations, for example, addition and convolution. Step number 2, we extend this ring to its field of fractions, which is an abstract algebraic abstraction whose elements are not necessarily functions. Step number 3, we express integral operators as ring elements via convolution. Step number 4, we express derivative operators as field elements via inversion. And finally, the step number 5, we are now all set to transform differential equations into the algebraic equations. And after some algebraic manipulations, we can easily recover the required solution. So let's have a look at these steps one by one. First, we choose the function space C0 infinity, which is the space of continuous functions defined on the interval 0 infinity. So this space forms a commutative ring without multiplicative identity, with the operations plus and star. Here, this plus, that is addition, is defined here, which is f plus g of t is equal to f of t plus g of t. And the star operation is defined as f star g of t is equal to the integral 0 to t f of t minus tau g of tau d tau, the same convolution which we need in the theory of the Laplace transforms. Okay, so far we are done with the first step of the Mikusiński's algorithm. Now let's try to express the integral operator as an element of the ring. So for this, if we switch f is equal to 1 in this convolution relation, that is a constant unit function, we obtain L star g of t, which is equal to integral 0 to t g of tau d tau. Okay, now let's try to extend this ring, that is C0 infinity, to its field of extensions. And this field is formally defined as the set of pairs Fg belonging to this space, quotient by the equivalence relation, that is F1 G1 is equivalent to F2 G2 if and only if F1 star G1 is equal to F2 star G1, where the pair Fg are usually denoted by F by G. So this set is a field under these operations where the plus is defined as f1 by g1 plus f2 by g2 is equal to f1 star g2 plus f2 star g1 by g1 star g2. And the star operation is defined as f1 by g1 plus star f2 by g2 is equal to f1 star f2 by g1 star g2. So far we have chosen an appropriate function space, that is C0 infinity. We have expressed the integral operators as ring elements. We have extended the ring to its field of fractions. Now, let's try to express the derivative operators as field elements Y invariant. Here we have the important theorem proposed by Mikusiński, which says in the field of fractions M generated by the ring C0 infinity, the algebraic inverse of L, which is our integration operator, is the element S of the field M, which acts on differentiable functions as S star F is equal to F prime plus F of 0. Here, this F prime is just the first derivative of the function F. The proof of this theorem is straightforward if we consider a function f from the space of absolutely continuous functions defined on the interval 0 infinity. We obtain f of t is equal to integral 0 to t f prime of tau d tau plus f of 0, which is ultimately equal to L star f prime of t plus f of 0, where the this f is equal to L star f prime plus f of 0 L, but this time in the field M. So just multiplying this equation by S, which is L inverse, we can we obtain the required result. Okay. Until now, we have discussed the first 4 steps of the Mikusiński's algorithm. Now we are all set to solve some differential equations using this technique. Here we consider an n-term differential equation, which is written in blue. So using the repeated application of this theorem, we can easily write y in this form, and this field element involving S, which is not a function, can be rewritten in terms of S inverse, that is our integral operator, which is a function to get a solution y in the space C0 infinity. Okay, let's move on to the history of Mikusiński's operational calculus approach and some of its extensions, which are available in the literature and are very useful in solving fractional differential equations in different settings. The method of Mikusiński's operational calculus for solving differential equations is discussed in detail in reference number 3, which is in fact the original book of Mikusiński's. It has also been applied to partial differential equations and many settings as seen in the survey paper of Luchko. Mikusiński's operational calculus approach looks very similar to the method of Laplace transforms, and indeed they are formally equivalent. But Mikusiński's method is superior because it applies on a larger space even for functions which do not have Laplace transforms. For example, the functions which are not exponentially bounded. For more details, please see reference number 6. The applications of Mikusiński's operational calculus to fractional operators and fractional differential equations has been performed mostly by Luchko in 1990s with various collaborators including Haddad, Gurinflo, Hilfer, Tomasky, and others. Next, we have some basic definitions of fractional calculus. First, we define the Riemann Liouville fractional calculus with respect to functions. The Riemann Liouville fractional integral with order mu greater than 0 of a function f with respect to a function psi is defined in equation number 1. And the Riemann Liouville fractional derivative with order mu greater than 0 of a function f with respect to a function psi is defined in equation number 2. Next, we have the definition of the Mittag-Leffler function. The original Mittag-Leffler function with parameter 1 and of one variable is defined in this equation, and its generalizations to a 2-parameter Mittag-Leffler function and 3-parameter Mittag-Leffler function are defined in these equations respectively. Okay, let's move on to the main part of my talk. Now we will try to establish Mikusiński's operational calculus approach for solving fractional differential equations in the settings of Riemann Liouville fractional operators with respect to functions. Again, step number 1, we need to choose an appropriate space, and in this case, the space C alpha psi serve the purpose. For any given alpha belonging to a set of real numbers, a function f of x for x greater than 0 is said to be in the space C alpha psi if there exists a real number p greater than alpha such that f of x is equal to psi of x to the power p f1 of x, where this f1 is a continuous function defined on the interval 0 infinity. Here, this C alpha phi space is a vector space, and the set of spaces C alpha psi for alpha belonging to set of real numbers is ordered by the inclusion given in relation number 3. Okay, now let's step number 2. Let's try to express the fractional integral with respect to functions as a ring element. So for this, we have this relation which says fractional integral of f with order mu greater than 0 with respect to function psi is equal to this convolution, this generalized convolution, where this h mu psi is equal to psi of x to the power mu minus 1 divided by gamma of mu. Here, this generalized convolution, which we are denoting by star psi, is the generalized convolution operation which is defined in equation number 5. Unfortunately, we couldn't cite this reference number 5 in our paper that has been published at FCAA. In fact, we were not aware of the fact that this generalized convolution and the so-called generalized Laplace transform had already been studied by this Soviet researcher back in 1979. Next, we have another important result which says the fractional integral of order mu with respect to a function psi maps the space C alpha psi in itself. Next, we define an appropriate function space for the fractional derivatives. Function f of x for x greater than 0 is said to be in the space omega mu alpha psi if we have this inclusion under these conditions, and also this space is ordered by the inclusions given in these relations. Okay, now let's try to extend, let's try to make this C alpha psi space a ring. For the sake of simplicity, we just fix alpha is equal to -1. So this space C -1 psi with the operations of psi convolution and ordinary addition becomes a commutative ring, I mean ring without identity, without zero divisors. So far we have chosen an appropriate space which is a ring that is C -1 psi. So we are done with the step number 1. Let's try to find the extension, a field extension of this ring. So following Mikusiński's reasoning, this ring, that is C minus 1 psi, can be extended to its quotient field denoted by M minus 1 psi by quotienting this set with respect to the equivalence relation given in 6. And the elements of this field can formally be considered as convolution quotients denoted by F by G, where the operations of addition and multiplication in this field are defined in 7. And again, we have a very important result, which says the space M minus 1 psi with operations of addition and multiplication given in 7 is a field. Okay, up till now, we have found the field extension of the ring C minus 1 psi. Okay. Now let's try to find and try to express the Riemann Liouville fractional derivative of a function with respect to another function as a field element. So here we have this result, which says under these conditions we have equation number 9, which is an expression for the Riemann Liouville fractional derivative with order mu of a function f with respect to a function psi. And here we have expressed this derivative as the elements of the field f, M minus 1 psi. Next, we have an important lemma, which is very helpful in solving fractional differential equations in the generalized setting. I mean, fractional differential equations which are defined in the settings of Riemann Liouville fractional derivatives with respect to functions. So this lemma says the relations given in 1, 2, and 3 hold true between elements of the field M minus 1 psi and explicit functions of x in the function space that is our ring C minus 1 psi. Okay, now let's try to solve some fractional differential equations using this Mikusiński's operation, this newly constructed Mikusiński's operational calculus approach. Here in this theorem, in equation number 10, we have a differential equation. A differential equation in the framework of Riemann Liouville fractional derivative with order mu greater than 0 of a function y with respect to a function psi. In 11, we have the initial condition. So this initial value problem can now easily be solved using this newly constructed Mikusiński's operational calculus approach. Okay, here we just solved a very simple and only one term fractional differential equation. Next, we have another a bit more complicated differential equation, which is stated in equation number 13. Here we have an n term fractional differential equation, again in the settings of the Riemann Liouville fractional derivative of a function y with respect to a function psi. And in 14 and 15, we have the initial conditions. Again, using the Mikusiński's operational calculus approach, we can easily solve this system, this initial value problem. And the solution of to this problem is given in equation number 16. Let's move on to the final part of this presentation, that is conclusion. This work establishes a new extension of the concept of Mikusiński's operational calculus, already well known for classical derivatives and integrals, and also in the last 2 decades for fractional derivatives and integrals of various types. So this work is devoted to the extension of this mathematical formalism to the class of fractional operators with respect to functions. And we are well aware of the importance of these generalized fractional operators. So Mikusiński's operational calculus is a useful method for solving differential equations, formally similar to the method of Laplace transform. But this method is superior, also easier to justify rigorously and applicable in some problems. where Laplace transforms cannot be used. For example, I have already mentioned the functions which are not exponentially bounded. This presentation is based on the extracts of our paper, which has been published at FCAA in 2021. These are the references. Okay. During my talk, I used a term generalized Laplace transform. I'm sorry, I couldn't add it in my slides. So here is the expression for the so-called generalized yes, psi. So this is the definition of the generalized Laplace transform. And we can see that this is just the natural generalization of the classical Laplace transform. And I repeat, this Laplace definition of the Laplace transform and the generalized convolution operator had already been studied by some Soviet researchers back in 1980s or 70s. So this is not a new definition at all. And here in reference number 16, we have discussed the theory and its relationship with the fractional calculus with respect to functions. So thank you so much for your attention.
Okay, thank you, Hafiz, for interesting talk. So we have around 5-7 minutes for questions. Okay.
I'm sorry. Yeah. Here, here Mayor is basically the psi of x. That's why we need a psi prime of x here.
Hi,
Thank
Fahad. Nice presentation. I have just small questions. You said that Minkowski, this operation is better than Laplace, and it's more easy. So is there some sufficient conditions that it will exist just like we have in Laplace transformation?
Okay. Again, let's. Here is the algorithm. The only issue with this method is we use some concepts from algebra. So I think maybe it would be difficult to translate this theory in the computational methods. I'm not sure about that. I think other than that, there is no problem. There is no harm in using this method.
Okay, and one more thing, that you defined one operation f1 by g1 dot f2 by g2 is equal to some expression, and there is denominator, in the denominator there is g1 convolution g2. So please,
okay,
just can you come to that? Yeah, this one. So how can you make sure that this g1 convolution g2 in the denominator won't make any problem?
Here, this g1 and star g2 is here G1 and G2 are the elements of the ring, not the field. So we are basically focusing on here we are defining these two binary operations. So they exist. There's no problem with these expressions.
Okay, so it won't be never be zero. Okay. And can we solve PDEs with the help of this operation?
I have mentioned some references.
Mhm.
Yeah, reference number 4. Here in reference number
Okay.
4, the authors use the classical Mikusiński's operational calculus approach for solving some partial differential equations.
Okay, and you solved some equation for Riemann Liouville
Yeah, we
differential
only
operator?
use the differential equations, fractional differential equations in the settings of Riemann Liouville fractional operators with respect to functions.
Okay, so can we do that for other also? Means capital
Okay,
R or
we
that?
have another paper which is recent, which has recently been published at AMC, in which we made use of this operational calculus approach to solve fractional differential equations in the framework of Caputo fractional operators with respect to functions.
Okay, any other questions? Right.
So my question is on the definition of the generalized Laplace transform.
Yeah.
So you have this kernel, this function e to the minus s psi x. Can you find conditions for which you can express this function as a superposition of exponential functions with a spectral, so that you can go back somehow to the usual Laplace transform, but with weights somehow?
Okay, I'm sorry, I cannot answer your question because the terms you are mentioning, superpositions, etc., I am not well aware of these terms. Number one. Another thing which I would like to mention here the function f is we need a condition on f where the function f is now not exponentially bounded but psi exponentially bounded, which is again a natural generalization of the definition of exponentially bounded functions. That's it. Thank you.
I think what you're asking is about the relationship between psi Laplace and classical Laplace. Somehow, yeah. There is a relationship.
Yeah.
Not necessarily you can do it but you can write the computation relationship.
Okay. Also, we have something like this. I'm not sure either this relation is I wrote it correct or not, but you can find this relation and related theory to this relation in this reference paper. Here, another thing which I would like to mention that if we want to solve fractional differential equations, I mean generalized fractional differential equations, and we want to make use of this Laplace, generalized Laplace transform, we don't need any extra effort. We can just use this relation and some concepts of conjugation relation.
Okay. Well, we still have time for last question. It's very practical question because your title is calculus, operation calculus and its application. So for example, equation number 10, could you open please?
Yeah.
Yes, it looks like relaxation equation with some forcing. Could you give us convincing example why it's so important to study that equation number 10?
Okay, our focus in this paper and in particular in this presentation was to introduce a generalization of Mikusiński's operational calculus approach.
No, that's clear. But have you got some real application in your mind?
No.
No. Okay, thanks.
Thank you.
All right. Thank you very much. Oh. Yeah, that's what. And the meaning of function psi then? That's what my question. That's the reason I'm asking, because yes, it's a relaxation equation, and yeah, exactly. That's okay. Because my next question was about psi function, the meaning of it. I see. Okay, thank you. All right, thank you for a nice talk.